All right. The last part of Chapter 10 deals with molecular orbital theory. And it's a different way of thinking about how atoms come together to form molecules and how bonds are formed. It's a more powerful theory because it explains more things than what we have just been dealing with, which is valence bond theory. So in valence bond theory, we have what's called the localized electron model, localized electron bonding. We're saying that the electrons are on the atoms, and then the orbitals combine with each other, and that's how the electrons can get shared. And so we're always sort of looking at two atoms connecting together. Now there are more modern theories of valence bond theory, localized electron models that extend that a little bit. But what we've been talking about is just atoms kind of come together, smush their orbitals together, and make a bond. And that works out okay for some structures, but as we've seen, there are some things that it doesn't really work for. So for instance, NO was one that we looked at, nitrogen monoxide. If you try to draw a Lewis structure for that, you find that you have 11 electrons. So when we try to draw this, we can put a double bond here, and then we can go 1, 2, 4, 6, 8, 10, 11. So nitrogen doesn't have an octet, or we can put in a triple bond, and then we have more than an octet, or we can switch it over to oxygen. Oxygen doesn't have an octet, but basically there's no good way of distributing these electrons. And this is true for all of Lewis theory. It just cannot deal with any structure with an odd number of electrons. So and these structures exist. So to just say, well, this theory can't deal with anything except even numbers of electrons, already kind of discounts it a little bit, because that means that there's a huge collection of structures that it's not going to work for. So that's one way that valence bond theory, localized electron model, fails. The other way is with a much more common and simple molecule, O2, dioxygen. We can draw a Lewis structure like this. Okay, everything looks good. It's a nice, well-behaved Lewis structure. Everything seems to work nicely. It has a double bond, which is confirmed with experiment, that dioxygen has a double bond in the experiment. What gets weird, though, is that dioxygen is paramagnetic. Do you remember what paramagnetic means? Yeah. Yeah, it has unpaired electrons. So paramagnetic molecules, paramagnetic species are attracted to magnetic fields because they have unpaired electrons. So take a look at our Lewis structure there. Which electrons are unpaired? None of them, right? They're all paired. So that's a problem. We have a physical measurement that says for sure there are unpaired electrons in the structure. But our bonding theory says, no, everything's paired up. It's all good. So that's more evidence that this model of how we describe the bonding and how we account for where the electrons are in the structure is not quite complete. So we need a new theory. So the new theory is called molecular orbital theory. And the basic idea is that all the atomic orbitals in a molecule are going to combine to form what we call molecular orbitals. So then electrons will occupy these molecular orbitals. Which we call MOs. So instead of saying we have orbitals on this atom, orbitals on this atom, the atoms come together and the orbitals squish together to make bonds, we say when these atoms come together, we're going to think of the atomic orbitals as kind of making a big pool and then forming new molecular orbitals out of those atomic orbitals through what's called linear combinations, meaning adding and subtracting different orbitals together. And so what the electrons in the molecule, instead of saying, okay, these electrons are shared between these two carbons, all of the electrons are actually shared among the entire molecule in these molecular orbitals. And some molecular orbitals will be centered more on one side, in one place or another place, but in general, the electrons are delocalized over the entire structure. The word, again, is delocalized. So you have a local electron model, the localized electron model, which is valence bond theory. The electrons are kept in their spots. And then you have a delocalized model, which is the molecular orbital theory, where the electrons occupy these molecular orbitals that are spread out over the entire molecule and include lots of different atomic orbitals. Okay. So we're going to kind of look at this in two steps. First, if two atoms are going to come together, we have to form molecular orbitals from the atomic orbitals. Then we put the electrons in the molecular orbitals, and that gives us kind of the picture of the bonding of the structure. So we're going to start simple, as we usually do, with just diatomic molecules, just two atoms. So to construct molecular orbitals, we make linear combinations of atomic orbitals. Okay? Linear combinations mean adding and subtracting them together. So if we had hydrogen, H2, we would say that each hydrogen has a 1s orbital, right? That's what the bonding is? Okay. So our atomic orbitals are that we have two 1s orbitals. So to make molecular orbitals when the hydrogens come together, we're going to add and subtract those two orbitals. And of course, there's only two ways to combine them. We're either going to add them or we're going to subtract them. So the addition of the two orbitals gets us one molecular orbital, and the subtraction of the two orbitals gets us another molecular orbital. All right, so let's make two molecular orbitals. The first one is going to be the sum. So we'll call that sigma s. And so that's going to be the 1s from one hydrogen plus the 1s from the other hydrogen. And then we're going to we'll look at what that looks like in a second. And then we're also going to make, we'll call it the 1s. We're also going to make a sigma star 1s, and this is kind of the new weird thing, which is going to be the other linear combination of the two orbitals, so subtracting them from each other mathematically. Okay, so what does that actually mean in the structure? Well, in the structure, if we were to add two 1s orbitals together, that means that we're taking here this 1s orbital and this 1s orbital. We're adding them together, and we're making this. Now this looks a lot like our sigma bond from the previous section, our localized sigma bond. But this is not a sigma bond anymore. This is called a sigma orbital. This is a molecular orbital. This is a place where electrons can be that covers the entire molecule. And so just like with the atomic orbitals, we would say that you have a probability of finding the electron within this space, within this cloud. But now this cloud spans the entire molecule instead of just being centered on an atom. The subtractive one is a little bit weirder. Because when you subtract two orbitals, it might seem like they just disappear or something, right? Because you're taking something and subtracting itself. But because these orbitals have phases, a positive or negative phase, what you're actually doing is you're adding the inverse, or you're adding the negative version of one of these. And so you end up with a kind of weird-looking molecular orbital, and we'll use a shaded versus an open orbital to show that you have this difference in phase, which gives you a node in the middle, an area of 0 electron density. And that's what we call our sigma star orbital. So this first one, where everything combines nicely, we refer to as a bonding orbital. And the second one, where we've created this node and we've subtracted this thing, we call an antibonding orbital. And one way you can think of it, it's a little bit of a simplification, but one way you can think of it is that bonding orbitals promote connection within molecules, and antibonding orbitals promote dissociation in molecules. So if electrons are filling bonding orbitals, that's causing the molecule to hook together more. If electrons are filling antibonding orbitals, that's causing the molecule to break apart more. So we'll be able to see, depending on where the electrons end up, if that molecule is likely to stay together or to break apart. And that's how we decide whether something is actually a bond or a single bond or a double bond or whatever. Okay, so that's how we make our linear combinations. And then we set up something called a molecular orbital diagram to show where the electrons go. So in a molecular orbital diagram, we're going to start with the two individual atoms on each side. So we'll have a hydrogen on one side and a hydrogen on the other side. And then in the middle, we have the molecule, which in this case is just HH. So we're going to list the atomic orbitals on the outsides, and we're going to base them on energy. So going from low energy to high energy. This is another color here. All right, so here is one hydrogen orbital, that's our 1s. And here's our other hydrogen atomic orbital, 1s. And those orbitals also each have one electron because each hydrogen has one electron in its 1s. We're only going to really deal with the valence orbitals here. Okay. So now we have to construct our molecular orbitals. Remember, the molecular orbitals are the two linear combinations that we found, the bonding and the antibonding. The bonding is lower in energy, it's more stable. The antibonding is higher in energy. So we put our two molecular orbitals in the middle, our sigma and our sigma star. And then it's usually customary to show which atomic orbitals contribute to which molecular orbitals. So in this case, both molecular orbitals are formed from both atomic orbitals. So we kind of draw some dotted lines showing that. And that's our molecular orbital diagram. Our very last step then is to take all the electrons from the structure and use them to fill the molecular orbital diagram from the bottom up. So we have two total electrons, and they both end up in the sigma 1s molecular orbital. All right, so what can we learn from this diagram then? Well, one thing that we can look at is called the bond order. And our bond order is 1/2 times the number of bonding electrons minus the number of antibonding electrons. So in this case, our bond order is 1/2 times, we have 2 electrons in a bonding orbital. That's the sigma 1s. And we have 0 electrons in an antibonding orbital. So our bond order is 1. And bond order in these types of molecules is comparable to what we said in the Lewis structures about single or double or triple bond. So a bond order of 1 means single bond. Now the power of this method is we can look at different structures and different possible things and fill the electrons up in different ways and then make some decisions about the stability of that molecule. So let's look at helium instead of hydrogen. What if we had, how would this diagram change if we were looking at a dihelium molecule, He2, instead of a dihydrogen molecule? What's the difference? Let's think about the different things. So would the orbitals be different? The orbitals would be the same, right? Because the valence electrons in helium are also in the 1s. So those orbitals would be the same. Okay, so that means our whole diagram basically is the same. So if we want to know what's going on in bonding for helium, for dihelium, we can just kind of copy that exact same diagram. What's going on here? I'm running out of memory or something. Right, so we don't even really have to think about it. We don't have to construct new combinations or whatever. We just know that whenever there's 2 s orbitals, they're always going to combine in this way. They're going to make a sigma and a sigma star. So what does change here? The number of electrons. Now each helium comes with 2 valence electrons. So when we fill up our molecular orbitals, we're going to take all 4 of those and fill them from the bottom up. 1, 2, 3, 4. And then when we calculate our bond order, we've got 2 bonding electrons and 2 antibonding electrons. And so our bond order is 0. And bond order of 0 means no bond. So in this way, the molecular orbital diagram predicts that there should not exist a He2 molecule, and in fact there doesn't. But now let's think about this. What if we were able to make a molecule like this that was ionized? So what if we took some electrons out of a molecule like this? And this is another way that this theory is much more powerful than what we did before. If we want to know the bond order of an He2 plus 1 molecule, a molecular ion, that's pretty simple to do. All we have to do is remove 1 electron from our molecular orbital diagram. We ionized it. We took 1 electron away. So now our bond order, instead of being 2 electrons in the antibonding, we now have 1 electron in the antibonding. And so our overall bond order is 0.5. So that means that we should expect some kind of association between 2 helium atoms if we ionize it, if we take an electron away. And that's a thing that would exist, that we would expect to exist. So if we look now at an He2 2+ ion, if we took another electron away, would that stabilize the structure or destabilize the structure overall? It would stabilize it because we're taking electrons out of the antibonding. So the more electrons in the antibonding orbital, the less connected that molecule is. You take electrons out of the antibonding orbitals, then you make it more stable and more connected. And that's an idea that we have no analog to with Lewis theory. You can't draw a Lewis structure of He2 at all. But even if you could, there'd be no way of dealing with like what happens when you ionize things and all of this stuff. All right. So that's basically how this works. Let's look at what happens when we get a little bit more complicated. We get into the n equals 2 level, and we start dealing with p orbitals. So I'm going to pull up some pictures from the book here. All right. So in the 2s, you can see the picture in the book here, the 2s is going to look the exact same as the 1s. In fact, all s orbitals are going to work basically the same way at this approximation, where they combine and they make a bonding orbital from the sum and an antibonding orbital from the difference. P orbitals are going to do the same thing, but because there's 3 of them and they're oriented differently, things are going to look a little bit different. So when 2 p atomic orbitals that are parallel to each other, or what do you call that, next to each other, pointing at each other, combine, they're going to form a bonding orbital that kind of looks like the sigma bond that we drew before, and an anti-bonding orbital that's kind of like the opposite of that. So the middle kind of goes away, and the outsides get bigger, and the phase is different. The book uses blue and red to identify like the 2 phases, because they're not really positive and negative exactly. They're just different phases because they're waves. So so in phase or out of phase. So there's our node in the middle, and it kind of looks like with the s orbitals. With the other p orbitals, the parallel ones, we make pi molecular orbitals that look like the pi bonds we saw before, or kind of related to the pi bonds we saw before. So that's what one would look like. You've got the parallel p orbitals making a pi bonding orbital and a pi star anti-bonding orbital. And then you have the third set doing the same thing, but just in the perpendicular direction. Like that. So that gives us three sets of p orbitals. But the good news is they'll always combine in basically the same way. So once we know how p orbitals combine, any structure, any diatomic molecule that's combining its p orbitals is going to combine them in approximately the same way. So we can say that we have our 3 degenerate 2p orbitals on each side. No? Okay. That's fine. And those are going to make a sigma and a pi that are lower in energy. 2 pi, and there's 2 of the pi's because there's one that goes this way and there's one that goes this way. And then those are going to have their mirror on higher energy with the antibonding versions. So we've got the pi star and the sigma star. And then we do the same thing as before. We would fill with however many electrons we had. This is the standard molecular orbital diagram for p orbitals. But there is one thing to note, especially if you're doing the homework in the book. These two switch places in diboron, dicarbon, and dinitrogen. So the pi, kind of, the sigma ends up higher in energy than the pi. But like all other structures that you'll see, well, the ones that we'll do with different atoms and things like that, that's the standard diagram. All right, so let's now show how this explains that second question with our last 5 minutes, how dioxygen ends up being paramagnetic. Okay, So I'm going to pull in a diagram from the book here because, again, once the diagram is constructed, we don't need to keep rebuilding it from scratch. We can just say, okay, this is what it looks like for this type of a shell, for this type of a molecule. So here's our molecular orbital diagram for most diatomic molecules, except for there's going to be a slight difference in those three that we listed above. So you've got your atomic orbitals on each side and your molecular orbitals through the middle. The 2s forms the sigma and the sigma star, just as we did before. And then the 2 p's form the sigma, the 2 pi's, the 2 pi stars, and then the sigma star. All right, so now we can fill that up with electrons. So let's use an actual example here. Let's take oxygen, dioxygen. So we're going to have an oxygen atom over here, an oxygen atom over here, and then in the middle we have O2, we have our molecule. How many valence electrons from each oxygen? 6. So we'll go 1, 2, 3, 4, 5, 6. We know that's the electron configuration for oxygen. Same thing on the other side. All right. So now we pull all those 12 electrons together, and we fill from the bottom up. So we just go 1, 2, 3, 4, 5, 6, 7, 8. We're not going to pair those yet because whenever we have orbitals on the same level, we always distribute the electrons before pairing them. Then we go 9, 10, 11, 12. Okay, so there's our 12 electrons. We can calculate the bond order. Remember, it's bonding electrons, or electrons in bonding orbitals, minus electrons in antibonding orbitals. The bonding orbitals are the sigmas and the pi's, so that's 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 electrons in bonding orbitals. And then how many electrons in antibonding orbitals? We've got 2 here and 2 here. And so our bond order is 2. And that actually fits with our Lewis structure, with our valence bond description, that we have a double bond between oxygen atoms. But the molecular orbital diagram also explains the observed paramagnetism, because in the molecular orbitals, we have unpaired electrons. So we have one unpaired electron in each of the pi star 2p orbitals. And remember, these are molecular orbitals that span the entire molecule. So those electrons, according to this, are indeed unpaired, and that mirrors the physical observation that this molecule should have unpaired electrons. So in general, molecular orbital descriptions have kind of taken over as the dominant form of how to describe bonding. Now there's actually an interesting revert back a little bit to the valence bond theory, because now we have more powerful computers and we can compute these with more degrees of freedom, what those orbitals might look like and what interactions between 2 or 3 atoms might look like. But molecular orbital theory is very powerful. It can be scaled to much, much larger molecules. So when we look at some examples in the book here. Oh, you know what? They don't actually show it in this book. I think in our book they do. But you can have very large molecules. You can put the orbitals into a computer program and ask the computer to calculate the molecular orbitals. And you can see over the entire molecule where are the bonding and antibonding orbitals. You can use that to predict geometries, to predict stability, and even to predict reactions. So how will 2 molecules interact with each other? We can calculate the orbitals and determine there's like more electron density over here in this one, there's less electron density over here in this one, and so that's where we expect them to connect. These types of calculations are used in things like protein docking to find new drugs that will fit and disrupt proteins. You need to know like where those electrons are going to go. So it's an extremely powerful theory. This is about as far as we're going to take it in this class. There are some practice problems in Chapter 10 where you'll construct some diagrams like this and fill them with electrons. And you'll see that on the next exam also, but we won't go beyond diatomic molecules. So we'll focus on just where there's two atoms. Makes the diagrams a little bit easier to construct.
How do you know where to start these? Like, what about the 1s?
The 1s is not valence electrons. So bonding only is going to deal with the valence electrons. So whatever the valence shell is, that's all you have to deal with. Now it is true that d orbitals are involved in bonding. And so if we were trying to construct things with the d orbitals, those would start to be involved in there, but that gets a little bit more complicated, so we're not going to deal with that in this class. Yeah, but you're just looking at the valence electrons. So for our purposes, it's always just going to be the s and the p from the valence. All right, sound good? So tomorrow is our continuation of last week's lab, and we will be taking some NMR spectra and interpreting some NMR spectra. There will also be, there's only one NMR, so there's going to be a little bit of downtime, so there will be some stuff to do in here while you're waiting for your turn on the instrument. Hopefully, I think by the end of the class, everybody got some good products, so we should be good to go for that tomorrow. All right, see you then.